All right, thank you very much for the warm welcome. Again, my name is Mark Zhao. I'm an undergrad at Cornell, and this work was done alongside my advisor, Professor Ed Suh. So again, this talk, I will talk about how introducing FPGA integrated systems introduces new vulnerabilities that may allow attackers to perform remote power side channel attacks. And this is important now as we enter an era of pervasive hardware specialization, in which we're seeing a lot more prevalence of hardware accelerators in both cloud and mobile computing. And one form of hardware acceleration comes as a field programmable gate array, or FPGA. And what these FPGAs are is that they're simply a fabric of reconfigurable logic blocks connected with some programmable interconnects, and users can use RTL code to implement virtually any circuit in the FPGA devices. And this is very minimal towards data center workloads, which rapidly change. So for example, two recent projects that came out are Microsoft Project Catapult, in which almost every new Microsoft server is integrating a field programmable gate array. And secondly, Amazon EC2 F1 instances, if any of you guys have used them, which allow public users to program their own device on a cloud-based FPGA. And furthermore, there's been a lot of proposed work that has proposed virtualizing or sharing FPGAs with multiple users. So the problem that this proposes is the fact that users have very fine-grained control over the FPGA hardware. And this may allow some users to abuse circuit-level vulnerabilities in an FPGA. In this paper, or this talk, we show how we can use these vulnerabilities to perform a remote power side channel attack, in other words, without any physical proximity to the device itself. So as an outline for this talk, I first will talk about how we can program such power monitors on an FPGA device. And I'll talk about a FPGA to FPGA power analysis stack, followed by an FPGA to CPU power-based timing attack. So just as a bit of a background on power analysis attacks, a traditional power analysis attack works like the figure on the left, where an attacker is assumed to have full physical control over the target device. The attacker then measures the power consumption of the device using a lab bench oscilloscope, which then gives him or her a trace as shown on the right. Using this power trace, the attacker can then infer confidential information that the device is processing. In contrast, our attack assumes no physical proximity to an FPGA. We only need the ability to program an FPGA. And how we do this is we build on the fact that the propagation delay of a signal throughout CMOS logic reflects the power consumption of the full device itself. This is because more power consumption results in more current flow through the device, which then leads to voltage drops in the power distributed network because of phenomena called IR and DIDT voltage drops. Now, these transient voltage fluctuations then change how fast signals propagate through CMOS logic. So so we show that in our case, we can digitize these propagation delay values using a ring oscillator, or RO. So the picture on the bottom shows a ring oscillator. It is simply an AND gate connected to an inverter, which is then looped back on itself. So when the enable signal of the RO is 0, then the circuit is static and nothing happens. However, if we enable the ring oscillator, we see that a signal propagates around the ring oscillator, and every oscillation, the output value flips. So if we just simply look at the output, it looks like a square wave. The insight is if there is more power consumption, this results in a reduction to the supply voltage. And in turn, this changes how fast, or actually reduces how fast these ring oscillators oscillate. And it will look like the square wave to the right. So if we connect a ring oscillator output to the clock of an up counter, and we let this counter run for, say, t seconds, after t seconds, if we read the output of the counter, we have a digitized value of our propagation delay. So for example, if the voltage supply is high, then we might have a count of 4 as shown on the top. If the voltage supply is low, which means more power consumption, we might have a lower counter value. So just to show that our conjecture works, we implement a network of 20 ring oscillators on a Z board or a Zinc 7020 system on chip. And alongside those ring oscillator power monitors, we implement 16,000 instances of a power wire circuit as shown to the right. So this power wire circuit is pretty simple in the sense that if you just enable the signal, then it consumes dynamic power. If you don't enable it, then it doesn't do anything. And as you can see on the graph, as we enable an increasing amount of power virus instances, then the oscillation frequency of these ring oscillators decreases linearly with a pretty good fit. So now that we can implement remote power monitors, let's see how these can be used for some attacks. So as I mentioned before, there's been works that proposed virtualizing FPGA. So for example, we might have a case as shown in the figure below in which there's a victim that is co-tenant alongside an attacker and on one physical FPGA device. So traditional isolation mechanisms in these FPGA devices will prevent the attacker from directly reading any secret information processed by the victim. However, through this side channel, confidential information may leak to the attacker and this isolation mechanism is broken. So to make this more concrete, we demonstrate this by implementing a 1024-bit RSA crypto engine on our FPGA, which uses a square multiply algorithm. So square multiply iterates through all 1024 key bits in a for loop. And the key thing to note is that in the red box, if that conditional is true, then our module has 2 multipliers computing at the same time. If that conditional is false, then only 1 multiplier is running, which means less power is consumed. So if we run this module explanation module on the FPGA and use our ring oscillators to record a power trace, we see in the power trace to the right that not only is every round of this RSA decryption visible, but the actual bit value computed during each round is also visible, meaning that a simple power analysis or SPA attack is perfectly viable. Now, there are potential FPGA security mechanisms that have already been proposed. A prior work has proposed that an untrusted module and a trusted module can be isolated physically by a moat of unused logic blocks. And we implement this scenario as shown on the picture below, and we call it ISO. Alternatively, a data center provider may restrict the user to only use RTL. In other words, the user cannot define where they place their ring oscillators. They can't define the routing between any logic in their circuit. We implement this and denote it as no PR. We show that in either case, our attack is still viable. So as you can see in our paper, we run 10 1024-bit keys through our RSA decryption engine, and we record and automate a SPA attack on each key. With our baseline case, where we have control over the placement and routing of our ring oscillators, it takes on average 3.7 traces to recover all 1024 bits of all 10 keys. In our physical isolation case, we still only need 8.9 traces on average to fully recover all bits of each key. In our no place and route case, that number increases to 11.4 traces on average. We can still see that this is a relatively low number of traces that is required to recover the entire key in all cases. So now that we've talked about FPGA to FPGA side channel attacks, let's move on to a CPU to FPGA attack. So a common device is an FPGA system on chip, and these devices integrate a hardened CPU, commonly an ARM-based CPU, onto the same silicon die as reprogrammable FPGA fabric. Unfortunately, these devices commonly share voltage regulator, which means that the CPU's power consumption is actually visible from the FPGA device itself. So for example, if we implement a secure string compare algorithm or process on one core of the CPU, and we assume that attacker has control over another core of the CPU alongside a portion of the FPGA fabric, traditional isolation mechanisms prevent any information from leaking directly from the string compare process to the attacker's core. However, through this voltage regulator, the activity of core 1 in this case is leaked to the FPGA logic, which then is directly communicated to the attacker's CPU core, which thus reveals the power consumption of the string compare process. And more so, we can see that timing information is leaked through the CPU activity itself. This is important because timing side channel attacks generally are built on variations in timing, and countermeasures generally assume that if computations are observably constant time, then there's no timing information leakage. However, these countermeasures frequently do not consider information leaked through CPU activity itself. So we can see how more concretely by implementing a RSA, the same RSA square multiply algorithm, but in software. In our case, we mitigate timing channels by delaying each iteration loop of the square multiply algorithm to the worst case where the conditional statement is true. So we can see in the power trace, an attacker can record a power trace of the CPU consumption. In this case, we show a 32 iterations of the square multiply loop. In this case, it's 16 zeros followed by 16 ones. Not only can you see each iteration of the square multiply loop visibly, you can also visibly see the bit value process during each round, thus leaking the secret key used by the RSA square multiply process. So our paper also shows that the ring oscillator is not the only way that we can exploit this side channel. We implement a delay line-based power monitor, as shown in the figure to the left. For the sake of time, I'm not going to explain how that works. But we show that the same attack can be performed on RSA. A concurrent work to ours uses the delay line-based power monitor or similar one to implement a similar power analysis attack on AES. And finally, another concurrent work demonstrates a crosstalk-based attack, which uses adjacently routed long wires to perform an attack on AES. So the question remains that what can we do about these side channels, these side channel attacks? Well, there has been a lot of work that has studied traditional power analysis countermeasures. For example, we can mask or hide the power trace of a confidential module. However, this incurs added overhead, especially in case of physically secure systems, such as data centers that data centers did not previously have to pay. Secondly, unique to data centers, data center providers can analyze the netlist and bit streams of incoming untrusted users to detect ring oscillators or carry chains used in delay lines. However, there are legitimate uses for ring oscillators, such as physically unclonable functions, and long delay lines look pretty much like long adder chains. And furthermore, analyzing these netlists is pretty computationally intensive. Finally, there is the option of simply not sharing the FPGA. However, this is an imperfect allocation of resources from users to actual physical FPGA devices. And furthermore, this doesn't really solve the problem of the current case where you have a user taking a lot of different IP cores from third parties. All of them are not necessarily trusted, and integrating that into their final design. And this still does not solve that problem. So thus, we believe a further amount of work is required in this field. So in conclusion, we show that FPGA fabric can be used to build multiple different types of on-chip power monitors. these power monitors are able to be programmed on FPGAs directly with no physical proximity directly through software. And these power monitors are able to be used to perform remote side channel attacks as well as covert channel attacks. And not only can they be used to attack neighboring logic on the same FPGA device, but we show that they can attack other components in an FPGA system on chip. So thank you for your time, and I'm happy to take any questions.
Thanks for your talk. Are you sure you haven't given a talk before?
I take that as a compliment.
Impressive work. Again, questions, please come to the mic. State name and affiliation.
Matthew Hicks, Virginia Tech. Great talk, as Kevin said. Great paper as well. I enjoyed reading it.
Thank you.
So we're in an interesting time where companies like Intel are now going to sell Xeon chips with integrated FPGAs on the processor itself, right?
Yeah.
How do you think your work impacts, regular operating system tasks where I have an underprivileged process now running? Can it spy on SGX enclave processes? Are they operating itself? Can it somehow impact these things using the techniques described in your paper? Right.
So yeah, I definitely think that is a huge concern. So I think our insight is not the fact that you can just do an SPA attack, but the fact that this side channel can enable a lot more different attacks. So we can do covert channel attacks. We can do, for example, as you said, attack SGX. We can use it, for example, identify what program is running on a process, which may compromise virtual machines, for example. And yeah, I think there's a lot more work to be done in order to kind of solve this integrating FPGA devices. And furthermore, there's also work on, for example, mobile devices where FPGAs are being integrated. We're having pros to be integrated into mobile devices, which again is a concern. I don't really know what the solution to that is, but that's why I think a lot more work needs to be done in this field.
All right, any other questions? Okay, well, let's thank Mark again.
Thank you.